on our topic of permutations and combinations, we looked at arrangements, but we also looked at all these different kinds of concepts like expansions and things like that, and how they're all closely related together. We're going to tie this all together again in our last topic called binomial distributions. Okay. Now, this word binomial, right? We've seen how that relates to the expansions of like two sums, right? But this concept of distribution, where have we kind of seen that before? It's actually something that's like kind of unrelated to the traditional expansions that we looked at. It was looking at when we were thinking about probability and the chances of things happening, but we were representing that not as just what's the chance of this happening, but we're actually kind of looking at graphs and things like that. And what does the distribution look like, so to speak, of all these different events? Yeah. So we're going to tie these two together now in something called a binomial distribution. And there's some terminology I need to kind of introduce. But the idea is that a binomial distribution has to look at a specific situation, has to only look at things involving success and failure. So that's kind of like thinking about two outcomes, right? Like, passing a test or not passing a test. What's the probability of these individual things? But you can also kind of take that a bit further, and you can look at like flipping a coin, right? If you were to translate heads and tails into success and failure, you could see success as like, flipping a heads. And then what would failure be? That would just be, yeah, so it would be tails, right? Exactly, but we have to kind of phrase it in a way that kind of makes sense in this new sort of context, right? Not flipping heads. That's the limitation, I guess, of a binomial distribution, right? So flipping heads, not flipping heads. We usually attribute the number 1 to the success and the number 0 to the failure. But like, it's not only limited to things with just two outcomes, right? Think about rolling a die. Like, how could you sort of translate that into this situation where we can create a binomial distribution from that? Because a die has, 6 outcomes, right? And you can do it, but you just have to think of it a little bit differently, just like we did here. So if we think about rolling a number, like rolling a 6, right? That could be your success, and not rolling a 6, right? So it's not that you can't do things that have more than 2 outcomes, but the way you phrase it and what probabilities you can find are kind of limited in that sense, yeah. Now, what I need you to do to start off with, though, is I want you to start seeing the relationship between probability and these expansions here. And you've got a little table that I want you to fill out. And the idea behind the table is we want to find how many kind of possible outcomes there are for flipping heads and their kind of arrangements, right? So let's think about if I want to flip, if I've got one coin, yeah? And let's go to this situation here where we're flipping heads. I've got one coin, and I want to know how many ways can I get, what's the first column? Is it 1 head or something like that? Yeah, 1 head, 0 heads. Right? So if I've got one coin, that's not particularly interesting. If you can get 1 head, you can just get 1. There's one way you can do to do that. How many ways can I get 0 heads? Also 1, right? Because I just get tails. 2 coins, though, that starts to add a bit of variation. So now 2 coins, we can get 2 heads, 1 head, 0 heads, right? So how many ways can you get 2 heads? 1? Yep. 1 head, you can get 2 ways, right? So you can get either, I'll put it in brackets, like heads, tails, or tails, heads, right? And then how many ways can you get 0 heads? Well, that's 2 tails, right? So that'd be 1 again. Oh, this is looking familiar, right? So you're already starting to see the picture. Can you go and complete the rest of them for me? 3 coins, 4 coins, etc. This little neat little table going on. Oh, you got it, Harry. Good man. Now, Matt mentioned something that this looks exactly like Pascal's triangle, and you're exactly right, yeah. And I guess the cool thing about this is that, when Pascal was developing his triangle, he was probably just playing around with numbers, right? Not without realizing that a lot of this stuff does have sort of applications beyond the concept he was looking at. You may wonder, hey, what's the interesting part about just finding how many heads I can get, right? Like, we're going to extend the application beyond that, obviously, right? But I do want to kind of give you some intuition about what's actually going on here, because when you look at the table, we learned that there's another way to represent these, right? So it's not necessarily just the numbers that are there, but also we looked at this notation here where we can have combinations representing these values. So I'll draw this out a bit neater. What you can see is if I have this over here, I want you to think about, I'm looking at things that have success and how many coins I'm flipping, right? So if you think about this first one, if I'm getting one head, right, there's one way that can happen, that's the tails. And sorry, if I'm getting one head, there's heads, and there's 0 heads, there's tails there, right? Another way you can think about that is you have one coin, right? And how many heads do you want? You just want one, so you're choosing one. Or if you want one tail, how many heads am I choosing? I'm choosing 0, right? Another way you can think about it, and as we keep going down, is, okay, well, if I have 2 heads, I have 2 heads to choose from now, right? How many heads am I choosing when I get 2 heads? 2, right? So 2 choose 2, yeah? If I want 1 head, then I'm saying, well, that's 2 choose one of them, so I can either have heads, tails, tails, heads, right? And then 0 heads, well, that's 2 choose 0, right? So can you see, this is a way to sort of generalize this approach, right? You don't have to draw out Pascal's triangle each time. What you can actually do is you can just think about, okay, how many coins do you have and how many of that particular success do you want? So how many heads do you want? For example, if we can go down all the way to 4, for example, if you want, did I make a mistake here? Yeah, did I? 1, 4, 6, 4, 1, and then that should be, what should that be? 1, 5, 10, 5, 10, 10, 5, 1? Looks better? Perfect. Yeah, there we go. Sweet. So we can skip all the way to 5 coins, for example, right? So the idea is, when we're looking at binomial distributions, I don't have to construct Pascal's triangle each time, right? I can think of it as saying, okay, if I have 5 coins that I'm flipping, right? I can have, like heads, 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 tails, tails, right? And the question is like the arrangements of that, what are you actually doing with this, right? Because if you think about it, you have 5 objects that are here, and you're kind of choosing 3 of them to be heads, right? That's where this notation comes from, 5C3, for example, right? So there's some intuition behind how this number actually comes about, and we're going to kind of need that later on. But I said that this topic is about probability as well. So we're going to generalize this for probability, not just saying the arrangements of things, okay? Because something else we want to consider is, okay, well, what's the chance of actually flipping a heads, for example? It's just half, right? So we can generalize our approach to the binomial distribution, and we can actually say that when I look at the probability of something actually occurring, not just the number of arrangements, I can generalize it like this. Do you want to jot that down for me? So this is the probabilities in a binomial distribution. I'm not 100% sure, actually.